On behalf of the speakers and the participants, I would like to thank the organizers, Professor Sejong Kwok and Youngnam Lee, for organizing this wonderful and very stimulating winter school. Thank you. And as for my last lecture, I'll talk about the second flip of MG bar. And most of the talk will be devoted to describing ideas behind the construction of the second flip. I should say that this is a joint with, this is current work in progress, which is joint with Jared Alper and David Smythe. I want to just introduce some notation that I will use later on. If X is a variety and D is a divisor, or X is a stack and D a divisor, the R will be the graded section ring of the divisor. And using this notation, let me remind you the definition of the log canonical model of MG bar, called MG bar of alpha. This is simply proj of the graded section ring of the log canonical divisor K plus alpha delta, where alpha is a rational number. Now for the, I will denote by UG the stack of all, this is an algebraic stack of all Gorenstein curves with ample dualizing sheaf. We can think of this simply as the, say, a quotient stack of some Hilbert scheme of curves embedded by their dualizing sheaves. And delta in UG will be the discriminant locus. So the discriminant locus, and these are locus of singular curves. All right. So now with this notation, let me state a principle which guides the log minimal model program for MG bar. It's not a result. We can think of it as a conjecture. I'd like to state as a principle. So the modularity principle which guides the current work in this program is the following. For each rational number between 0 and 1, there exists an open normal substack, which I'll call M script G of alpha. So this will not is different from the MG of alpha before, and this is a substack of UG. So it a stack of Gorenstein curves, and a map phi from the stack to the log canonical model. All right, so the relation between the two MG alphas is given by a map such that, and now let me list the conditions. First, phi is a good moduli map. So let me say what this means. This is in the sense of Alper. So see Alper And so what it means is that phi is bijective on closed field-valued points, and phi over star is the exact functor from the category of coherent sheaves upstairs to the category of coherent sheaves downstairs. Yeah, so this is just a technical condition, and there is a universality property with respect to maps from the script M to algebraic spaces. All right, so this is not really important, but we think of a good moduli map as a coarse moduli space map, or we can think of a good moduli space map as a map from a GIT stack, quotient stack, to the GIT quotient, which is usually which is a projective variety. Right, so this map is a good moduli map. In the case of a reductive group acting on projective variety X with the ample linearization. So this is an example. Right, so in something very familiar. Next condition is that perhaps slightly well, unnatural, but the one that seems to be satisfied in practice is that codimension of the locus of non-nodal curves. Right, so the nodal curves in UG are precisely mg bar, and so the codimension of the non-nodal locus is at least 2. And finally, we ask that the divisor, canonical divisor, plus alpha delta upstairs. Implicitly, so that's going to be a line bundle, and implicitly, I'm saying that delta is the Cartier divisor on mg bar of alpha. Descends to the right, which is O of 1 on the log canonical model. Sorry?
I missed the second item. Please say again, please.
This second property? The codimension of the non-nodal locus in mg bar of alpha. So it's some moduli stack of curves, and if we look at the non-nodal curves in this moduli stack, it has to be the locus has to be the codimension 2 or more. Okay. All right, so that's a principle. That's what we hope for. And in the cases when the log canonical model is constructed via GIT, this is precisely what one sees. Now, maybe as a continuation of the principle, let me state that we also expect that the transformations, the birational transformations between the log canonical models are of the form, the following form, namely at the threshold values of alpha where the model changes, we expect the following picture. So if alpha is a threshold value, then mg of alpha contains as open substacks both mg of alpha plus epsilon and alpha minus epsilon. And the resulting maps between moduli spaces induced by these open inclusions give rise to this diagram. So this is the good moduli space map, this is a good moduli space map, a good moduli space map here. And we expect the flips or contractions in the program to work like this. All right. Okay. And so let me give you an example of where this is actually, this is verified in practice, and an example which gave rise to the principle. So if we remember the definitions of the moduli spaces, mg bar pseudostable, which we can define as a quotient of the Hilbert scheme of the, say, four canonical curves. Hilbert scheme of genus G, four canonically embedded curves by this group. Sorry, EGL 7G minus 7. So this is a quotient stack. MG, we can define mg bar of 7/10 to be the quotient of the Chow variety of genus G, three canonically embedded curves by PGL, two canonically embedded curves by PGL 3G minus 3. And MGH semistable, which we've defined, can be constructed as a quotient of the Hilbert scheme of two canonically embedded curves, again by PGL 3G minus 3. And the spaces fit into a diagram like this. So this is a work of Brandon Hassett and David Hune. In which they show that the spaces fit exactly into the diagrams that I have over here for alpha equals 7/10. All right, so if I save some time and replace alpha by 7/10, I get precisely the flips between the moduli space of pseudostable curves and the moduli space of H semistable curves, constructed by Hassett and Hune. And so this is a picture of the first flip of mg bar. Now, moreover, so whenever we have an open inclusion of algebraic stacks which induces a regular map on the good moduli spaces, the only possibility, this is only possible when the closed points of the complement of the largest stack, the complement of smaller open substacks in the largest stack are curves with positive dimensional automorphism groups, have positive dimensional reductive automorphisms. In particular, they hence have a GM action, admit GM action. And indeed, in the example of the first flip, if one looks at the definitions of the moduli stacks of Hassett and Hune, one sees that curves which appear at 7/10 and which are neither H-semistable nor pseudostable are precisely curves which look like this. These are curves where we have, in general, this is a chain of P1s with the odd number of nodes. Sorry, tag nodes. And these curves clearly have a GM action which simply acts on each P1 by scaling, and where the action of the tangent spaces of tag nodes is compatible. So there is up to essentially up to power there is there is a unique such a GM action. Right. So basically, okay. All right, so now how do we go about constructing the next, the second flip of MG bar? And in particular, how do we know the value alpha at which it will happen? To describe the heuristic for determining the alpha value, let me quickly review the tautological line bundles on UG. Well, we have a UG with its universal family, pi. We have MG bar sitting inside of UG. And I'm going to denote by omega the relative dualizing sheaf line bundle of this family. And I'm going to define lambda 1 to be the determinant of the Hodge bundle, which exists over UG, and lambda 2 will be the determinant of the second Hodge bundle. Okay, there are two divisor classes, lambda 1 and lambda 2, and on MG bar we'll recall the relations. On MG bar, the following relations hold. First of all, lambda 2 is 13 lambda 1 minus delta. Delta is a Cartier divisor in MG bar. And also the canonical divisor of MG bar is 13 lambda minus 2 delta is 2 lambda 2 minus 13 lambda 1. All right, and so the modularity principle guides us to the kinds of curves that can appear in MG of alpha in the following way. We have a proposition. It's really a simple observation. So, assuming the modularity principle, if C is MG of alpha is a curve with a GM action, I'll write this as rho, so non-trivial map from GM to the automorphism group of the curve. Then okay, so I ran a little bit ahead of myself, and I apologize. me to make. Let me make a definition first. If C is a curve with a GM action, then define the two numbers. Chi1 will be the character of GM given by the action of GM on the determinant of this vector space, the top wedge power of the vector space of the sections of the dualizing sheaf. So GM acts on the curve, so it acts on the dualizing sheaf, it acts on this vector space. It's one-dimensional vector space, so it's just an integer. And chi2 is a character given by this vector space. Again, this is an integer. And I'll compute such an integer for a curve with a GM action. I'll show that these numbers are easily computed. And as a proposition is the following. With the assumption as before, if C is in MG of alpha, and this tag whose good moduli space is a law canonical model, which satisfies its three properties in the modularity principle, then the only possibility for alpha is the following. Assuming, of course, that the denominator is not 0. Well, assuming actually that the two characters are not 0 simultaneously. Okay, and so the way, so unfortunately I'll have to erase parts of the modularity principle. Maybe I can keep some for now. So how do we see, why is the proposition true? Well, proof let me using the assumption 2 in the modularity principle, the relation this equals to 13 lambda 1 equals to 2 lambda 2 minus 13 lambda 1 plus alpha. So this extends from mg bar because the relation holds on mg bar on the set of nodal curves, and mg bar of alpha is normal. All these line bundles are defined on mg bar of alpha, so the relation between the line bundles extends to the whole space. Right? It's true away from codimension 2, so it extends. And since by assumption this line bundle descends to the good moduli space, the character, the action, the GM action on the fiber of this line bundle is trivial. On the fiber 2 lambda 2 minus 13 lambda 1. I'll write this in the additive notation. This is a line bundle, and its fiber at the curve C is the action is trivial. And so what this means is that when we look at the corresponding character, it's 0. So what it gives us is that 2 chi2 minus 13 chi1 equals lambda chi2 alpha chi2 minus 13 chi1. Right, so this is essentially formality if we assume this very strong modularity principle. So nevertheless, although our assumptions are very strong, they guide us to correct conclusions. So let me work out an example of this character computation for a curve with a GM actions. I'm going to consider C to be the following curve. It's going to be a union of a genus G minus 2 curve with the rational component. The normalization is P1 with a singularity y squared equals x to the 5. So this is an A4 singularity. That's a called Ramfoid cusp. And right, and we have, so the equation of this tail is just spec of the rational component is just the projective closure of this Fn curve. And we have a natural GM action. So GM acts by like this. So we have a GM action on this curve. GM acts on via this. Of course, it acts trivially on the genus G minus 2 component. And so let's see what our proposition tells us about kinds of alpha values at which this curve can appear. We need to compute these numbers chi1 and chi2, the characters. Duality on singular curves tells us how to write the sections of the dualizing sheaf. So let S will be the uniformizer on the rational component. So we think of this as a spec of this ring. All right, then the sections of the dualizing sheaf are ds over and then where omegas are simply give a basis for the canonical system on C naught. Right, so the only interesting sections here are these two ones, on which we have a non-trivial GM action. And so the weights of GM action are, well, let's see. So GM acts on S with weight -1, and so the weight here is 3, and the weight here is 1, and the weights here are 0 because GM does not act on C naught. And so what this means is that on the determinant of this vector space, the GM acts with weight 4. So chi1 is 4. We can also work out the quadratic differentials, right, or rather sections of omega square, and these are, the basis for them is given by, we have squares And then let's see, okay. And there are more, namely there is one more with a pole at infinity, at infinity on the rational component. And the rest are just trivial on the rational component. Okay, 3g minus. How many do we need? We need 3g minus 1, 2, 3, 4, 5, 5. We need 3g minus I'll just check. Minus 8, right? And we need 3g minus 3. But I'll, okay. And unfortunately I forgot one more differential. And I guess this makes, okay, so let me write one more differential. This is ds squared over s cubed 0. Okay, so we have squares coming from here, but then there are some quadratic differentials which are not global squares. They are simply
because they have g
yeah.
minus 2, so should be 3g minus 3.
Should be
g minus 2. It seems to be 9.
It should be 9. And it does look to be, yeah, I mean, the total should be 3g minus 3. So we have 3g minus 9 and then 1, 2, 6. Yeah, okay. Yeah, okay, yeah. Sorry, and now,
Maksym?
yes.
Relating that part, is it that theorem, the closed point always has positive result?
Yes.
Kind of theorem or?
It's a theorem, yes. I mean, the point is if you have a closed point, then there is in this affine chart whose quotient by the automorphism group should be affine as well. That's a part of the good moduli space definition. Yeah, and then there is a theorem which says that the group then has to be reductive, and then and positive dimensionalities. I mean, also follows because you want otherwise that the point with the finite dimensional stabilizer will not. I mean, you cannot have the. Well, it follows. I guess I didn't ask for the small contractions on good on the log canonical models. They are surjective. I mean, so we want surjectivity of those contractions. So then you need positive dimensional stabilizers. But it follows from the picture. Yeah,
also, when you say the closed point here, so for example, the RK equals 7 over 10 case.
Yes.
In that case, this is a semi-stable point.
Yes, strictly semi-stable. So in GIT language, closed points correspond to strictly semi-stable with closed orbit, with minimal orbit. Yeah. All right, so let me finish the calculation. So the weights of the GM action are here 6, 4, 2, 0, 6, 4, 2. Six, 4, 2. Okay. There is. Okay. Well, there is an issue. I did not copy this correctly. Yeah. Okay. And I guess. So it looks like 8. I'm sorry. Yeah. Okay, should have just stick to my notes. So the GM weights are 6 plus 4 plus 2 plus 1, which is 13. And well, let's compute. So now the alpha value of this curve, I'll call it alpha of C. Yeah, okay. It's 2/3. It's 2/3. And now, well, we did many calculations like this, and there are no other singular curves with this alpha value. And in fact, in the interval from 2/3 to 7/10, there are no alpha values of curves with GM action other than the endpoints. But in the open intervals, there are no other alpha values which come from curves with a GM action. And this suggests that, I mean, that's one way to see that perhaps the next log canonical model appears at 2/3. Okay, this is a heuristic. There are other heuristics, and well, and this is, we're now writing up this result, that this is in fact so. To state the result, we need to make a few definitions. I mean, if we want to construct the next log canonical model, we have to give the definition of the moduli stack MG of 2/3. And this will be the stack of curves in UG such that C has at worst, well, I mean, y squared equals x to the 5. So this is A4 singularity. I mean, this singularity is deformed to tag nodes and costs. In particular, tag nodes and costs will be allowed. But this is the condition on the singularities. The global condition is that C has no elliptic tails, just as in the Hassett-Hune space. And the elliptic tails, to remind you, are curves which look like genus 1 component meeting genus G minus 1 component, but also genus G minus 2 component meeting tag nodally genus G minus 2 component. Like this. And also, as in the case of Hassett and Hune, we ask that C has no elliptic bridges. And so what are the elliptic bridges? Well, these are curves which look like this. A genus 1 component meeting the rest of the curve in 2 points. But also, and this is special to this alpha value, I mean, or this is the first time this condition appears, is that we ask that there are no curves which look like a P1 with a rhamphoid cusp. I'm sorry. A genus 1 elliptic curve with a rhamphoid cusp attached to a genus G minus 3 curve nodally. So these are not allowed. So these are both of those curves are called elliptic bridges. Okay, so this is a definition of the MG 2/3. It's not immediate, but it can be verified that this is an open substack of UG. So the claim here is that this condition define a deformation, that these conditions are deformation open. This can be verified. And a definition which is closely related is a definition of the next moduli stack. And this will be MG of 2/3. And now by our picture, we have to tell what to remove. We have to remove a closed substack. And we're removing a closed substack of Weierstrass genus 2 tails. So let me give a definition with a Weierstrass genus 2 tail. Genus 2 tail is definition by a picture. It's a curve which is a union of a genus 2, nodal union of genus 2 and genus G minus 2 curve, such that the attaching point on the hyperelliptic genus 2 curve is a Weierstrass point. So 2p is G1, 2. And the reason we want to remove the Weierstrass genus 2 tails at this point is that at 2/3 we introduce Rheinfeld cusps. And if one takes a curve with a Rheinfeld cusp and performs the stable reduction, the Lin-Mumford stable reduction, one obtains a curve with a Weierstrass genus 2 tail. So to preserve the properness of the next of this tag, we want to get rid of the genus 2 tails. Okay, they're still allowed at the threshold values. If one thinks in terms of GIT, then this curve becomes strictly semi-stable at alpha equals 2/3, and then both Weierstrass genus 2 tails and curves with Rheinfeld cusps isotrivially degenerate to this curve. Namely, their orbit closures contain the orbit of this curve, and then at different values of alpha, we throw out either one of these two closed loci. Okay, so one of those two closed loci are destabilized. So this is a definition, and now I'll state the theorem. So this is with David Smythe and Jared Alper. The theorem is that mg of 2/3 has a projective good moduli space isomorphic to isomorphic to mg of 2/3, the log canonical model. So this is a projective variety defined as a proj of some graded ring on mg bar, and this is the space that we've defined abstractly. This is the first part, and a related part here is that the log canonical model of mg bar remains constant on the interval from 2/3 to 7/10, and namely the Hassett-Hune space mg of H semi-stable curves is mg of alpha for alpha values of alpha from 2/3 to 7/10. Right, so this is namely there are no other alpha values in the interval. So let me just remark that part 2 is known in genus 4 already by work of Youngnam and David Hune. So the value, the fact that the value is 2/3 was known way before, and in fact they verified that this is it is. I mean, they verified in this in genus 4. It's also maybe expected or conjectured that the space mg of 2/3 can be constructed using finite Hilbert stability. Namely, if one takes the space of 6 Hilbert point of bicanonical curves, which I've defined in my first lecture on Wednesday, and one takes the GIT quotient, this is expected. Yeah, this is conjecture. Still wide open. This is expected to be mg of 2/3. Right? The GIT is really complicated, so we were in our approach we simply sidestep GIT stability analysis by guessing what the answer should be and doing a more Well, I'm using stacks instead of GIT. Okay, so I have time to describe ideas which go into the proof. And well, first, step one is the following. One shows that MG of 2/3 has a good moduli space. Lie space Y, and in general Y is just an algebraic space. It's not even a projective variety a priori. And this has been done by David and Jarrett earlier this year, last year, in a preprint in May. So they prove the argument is similar to, well, or is in the spirit to the argument of the Kilmury Theorem, which tells us that the Deligne-Mumford stacks, finite type over a field, have good moduli, coarse moduli spaces. This is a case of Artin stack. This stack parameterizes curves with possibly positive dimensional stabilizers, like this curve C. Okay. All right, so we have a good moduli space. And so what this means is that we have the following diagram. We have the stack. It's clear from the definition that H semi-stable curves are in the stack. So we have here a inclusion. Open inclusion. There is a good moduli space Y. We call this phi 2. There is a Hassett-Hune space, which is MG of 7/10 minus let me just call it MG of H semi-stable. And by the universal property of good moduli spaces, there exists, hence there exists a map F from this projective variety to this algebraic space. And from the modular description, F contracts families of Weierstrass genus two-tails, and in my notation was fixed C naught. Right. So what this means is that if you have a genus two-tail, which is Weierstrass, it's attached to a genus G-2 curve, then this simply maps to a curve with a Ramfoid cusp and whose normalization is C naught. So this map is regular. All right. So we know what curves F contracts. And now to obtain projectivity of Y and to obtain the second statement in the theorem, the key result is the following. Key proposition K MG bar H semi-stable. So I'm indicating on which space I'm working. I'm working on a space of H semi-stable curves. This line bundle is NAF and has degree 0 precisely on curves contracted by F. So let's assume the proposition for a moment and deduce the result. It's a corollary. Y is mg of 2/3, a log canonical model. So in fact, Y is projective, and also so the way the corollary, we establish the corollary is well, it follows formally from the nefness result and from the setup. Namely, we have a line bundle, right? So Km on our space M2/3 on the moduli stack. This line bundle has trivial characters on all curves with GM action. I mean, the reason is that the curves with GM action are precisely the Ramfoid hospital curves, where the Ramfoid cosp sits on the P1 component, on the rational component, and we've computed that the character of this line bundle on those curves is just 0. So this is a computation that we've done, and so what it follows that this line bundle descends to the good moduli space. It's a property of the good moduli space, right? It's the in GIT this is called the Kempf's descent lemma, and so Kmg 2/3 plus 2/3 delta is a pullback via good moduli space map of some line bundle L. And now we will study the positivity of L. If we pull back L via F and pull back it to the functor, this becomes this divisor, which by proposition is Nef. It's not hard to verify that it's big. Follows from Hassett and Hume construction, and therefore by, say, Kawamata base point freeness theorem, or by the fact that this divisor also has finitely generated section ring, this follows that this divisor is semi-ample. In particular, L is semi-ample. And has degree and has positive degree on all curves, right? Because its pullback had non-negative degree on all curves and had degree 0 precisely on curves which were contracted by F. So when we push forward the pullback of L, we get a semi-ample line bundle which has positive degree on all curves. And therefore, L is ample. Right. So this is a conclusion. Now, well, so what it means that L is ample, it means that Y is a projective variety. It's a product of the section ring of L. L pulls back via the F. F is just an algebraic fiber space to well, essentially to to here. L pulls back to on the stack of H semi-stable curves to K plus 2/3 delta, which by discrepancy computation is a product of the section ring on mg bar of kmg bar plus 2/3 delta. This is a discrepancy computation, and by definition this is mg of 2/3. And so this is a discrepancy computation. And also we know that K plus 2/3 is NF, plus the fact that by Hassett and Hune, K plus 7/10 minus epsilon delta is NF, is in fact ample, implies that K plus alpha delta is ample for alpha in the interval from 2/3 to 7/10. So we've established both parts of the corollary, right? Which completes the proof of the theorem. Modulo is a key proposition, and let me say how the techniques one we use to prove the key proposition are essentially standard. Modulo is the stable reduction arguments, which I won't go into. So proposition is, to establish the proposition, we modify it slightly. Namely, we observe that this divisor, well, it's everyone can observe this, but this divisor can be written as 39/4 lambda minus delta, or this is the tautological divisor classes. And we modify the key proposition as follows. Instead of working on MGH semistable, we work on a more general space of n-pointed H semistable curves. And proof uses work of Cornalba and Harris, the Cornalba-Harris inequality in genus greater or equal than 3. It essentially says that A plus 4 over G lambda minus delta is positive, and when G is greater than 3, that gives us what we need. It uses work of Smythe in genus 1, modular compactifications of elliptic curves. Genus 0 is standard, and finally in genus 2 we can use, the result is we need comes from Hune and Lee, for example. And I don't I'm not going to prove the key proposition. It's really the basically intersection theory in one parameter families and a very careful analysis of the positivity of those divisor classes. Okay, well, thank you very much.